Hello, everyone. This is the lecture for section 3.9, the derivative of exponential and logarithmic functions. So this is the last set of families of functions of derivatives that we need to pick up. And one more process in terms of how to take the derivative of some stuff, where we're going to need to use logarithms, okay? And then this will close out sort of us being able to just take a derivative in terms of an operation, right? At this point, after this section, we'll know how to take the derivative of nearly anything that gets thrown at us. So that's great, okay? In chapter 4, we're going to start using applications of all of these things, okay? So we're going to move away from like just rote computation toward actually using this calculus to do some other stuff, okay? All right, so let's go ahead and define some of these derivatives. Some of these are very easy. This one's probably the easiest one of them all. The derivative of e to the x is e to the x. So the derivative of e to the x is itself, okay? The derivative of the ln of x is 1 over x. The derivative of b to the x is that right there. And then the derivative of log base b, whatever that b is that right there. So it's the same idea as the derivatives before. These are the rules. There are proofs for them. I'm not going to go through them. I'd rather you just learn how to use them for now, okay? And just how we did with trig and inverse trig formulas, same thing with these, you know, these are sort of placeholders. Whatever is the x, that also has to, you know, sort of carry along if you're going to be doing a chain rule, okay? Okay, so let's go ahead and I'm going to do this example that's right here below, okay? So for this one, notice that it is a product, so we need a product rule, right? So I'm going to call it first and second. So my first is the x squared. The second is log of x cubed plus 2x plus 1. Okay, so then f prime, the derivative of the first is 2x, which means, and the second derivative, the derivative of the second, we're going to be using this one, right? And we know that this is log base 10. Okay, this is log base 10. Since it's not written, we can assume that it is log base 10. So we have, according to our rule, right, 1 over the thing in the parentheses, so x cubed plus 2x plus 1 times ln of 10, right? And since this right here is a chain rule, I have to multiply it by the derivative of the inside, which is 3x squared plus 2. Okay, so now I can clean this up a little bit. Let's go ahead and clean that up. So let's say 3x squared plus 2 over x cubed plus 2x plus 1 times ln of 10. Okay, now let's go ahead and find the derivative. Okay, and in order to find the derivative, like I said, this is product rule. So f prime of x is the first times the derivative of the second. So it's going to be x squared times this mess right here, 3x squared plus 2 over x cubed plus 2x plus 1 times ln of 10 plus the derivative of the first times the second. So 2x times the second log of x cubed plus 2x plus 1. And we are done. This is our derivative. Okay. Keep a track of everything. This has happened more often than not where, you know, I don't follow along with something, or I forget a value and then I have to go back and double check. You just keep double checking stuff. It's bound, you're going to mess up a bunch of these derivatives. It's not, you know, the calculus that's messing you guys up. It's the algebra. It's the arithmetic. It happens. Just double check. Okay. Let's keep going. So here's the quick checks. Make sure you do the one that's pertaining to you. Okay. I'm going to have you guys do another quick check. We're back to problems that you can check using the calculator. So if you can use the calculator that I provided, I believe it's in section 3.3, please do so. Okay. All right. So I want to get into this thing right here. It's called logarithmic differentiation. So this is going to require both our logarithmic rules that we just figured out, okay, and some implicit differentiation. I know that section was pretty difficult for people, but it's very helpful when we have to take derivatives of things that we really don't have rules for, okay? So the big part about logarithmic differentiation, okay, is that it doesn't matter what sort of functions or what values you have, right? If you take the logarithm of two functions or two values, they preserve order, they preserve a relationship. So what do I mean by that? Let's say, let me repeat that really quick. Let's say you have an f of x and g of x, and they have a certain relationship, whether it be any one of these, greater than, not, greater than, less than, not equal to, whatever. It doesn't matter what kind of relationship it has, okay? Then taking the logarithm of f of x and g of x, right? So taking, you know, whichever logarithm, ln, log base 10, log base 2, okay, whatever, preserves that relationship, okay? It preserves the relationship. So if f of x was greater than g of x, then the logarithm of f of x is going to be greater than the logarithm of g of x. That's the greatness of taking the logarithm, okay? To make it even better, logarithms preserve the relationship, right? And we can use all of our logarithm rules that we learned way back in pre-calculus. So first thing I want to do is just revisit a couple of these, okay, that we're going to use. This one, basically, this one and this one, basically say it's sort of like if you take b to an exponent, right, or log base b of something, then they cancel. Basically, this is what most people call the cancellation rule between logarithms and exponents. Basically, the log and the exponent, base b, of course, cancel out. You get just left with x, okay? A couple big ones that we'll use in the procedure are the product rule for logarithms. So if you have two things being multiplied inside of a logarithm, then you can split them up under an addition. If you have two things that are being divided under a logarithm, then you can split them up under a subtraction, okay? One more that we probably are gonna need more often than not is this one right here. That if you have a log base b of anything to some power, okay? So notice that this thing has a power n right there, right? Then all that gets to happen is basically you can bring the n out front. So that's why you can do that thing, okay? Don't confuse these with the derivative rules. I know it's easy to do that. And then the very last one that we'll be seeing is this one, log base b of 1 is equal to 0. So the log base anything of 1 is always going to be equal to 0. Okay? Okay. So what I want to do now is I want to show you guys how the hell this is useful. Okay? So in a second. Okay. So let's go ahead and go to the example here. Find the slope of the tangent line of f of x equal x to the sine x. Notice how we have a variable, right? And that variable is in the exponent under another fraction or another function, right? So at the moment, any of the rules that we have used right now make this absolutely horrible. We won't be able to take the derivative of this, right? So we're going to need some form of logarithmic differentiation to actually find the derivative for it. And this is one of the very first times that we're going to be seeing that we're going to use logarithmic differentiation and implicit differentiation to get our answer. So let me go ahead and run through this. The first thing I'm going to do is I'm going to call my f of x, I'm just going to call that y equal x to the sine of x. Okay. Here comes the logarithmic differentiation portion. Okay. I'm going to take the ln of both sides. Okay. It doesn't matter if you take the ln of both sides or the log of both sides. ln is just the easier one to mess with. So I'm going to do ln of y is equal to the ln of x to the sine of x. Okay. Now, on the right-hand side, I have something to an exponent inside of a logarithm. That's where we're going to use that product, that power rule from logarithm. So I'm going to rewrite this as ln of y is equal to sine of x times ln of x. You guys see how useful that became there, right? Okay. Now I'm going to be using implicit differentiation. I'm going to take the derivative of both sides, okay? And I'm going to do it implicitly. So I'm going to have a y prime sort of floating around here, okay? So the left-hand side, the derivative of the left-hand side is going to be, we know what the derivative of ln is. We go back up to the, actually, yeah, let me go back up to the top. The derivative of ln is 1 over x, right? So I get to do that here. So this is going to be 1 over y. I'm taking the derivative of y, so this is going to be times y prime is equal to, I have a product here, which means I got to do the product rule. So it's going to be the derivative of the first times the second plus the first times the derivative of the second. So the derivative of sine is cosine of x times the ln of x plus the derivative of the second times the first. So sine of x gets to stay times the derivative of the second, 1 over x. I have a 1 over y. So for the whole thing, I get to multiply this side by y. That'll cancel these out. Since I multiplied it to an entire one side, I get to multiply this by y as well. So then I get this, y prime is equal to y times cosine of x ln of x plus sine of x over x, right? Now, remember, I know we have a y sort of still floating around here, but y we made equal to, if you guys remember from the very beginning, we made that equal to the thing itself. So my derivative is going to be completely cleaned up here. X times sine of x times cosine of x ln of x plus sine of x divided by x. And we are done, at least with our derivative, right? So we still need to find the slope of the tangent line. Same thing applies here. Since this is the derivative, we can just go ahead and plug in our x value. So I am going to go ahead and plug my pi over 2. My pi over 2 into my function. So it's going to be pi over 2 to the sine of pi over 2. I'm writing it out first. We'll worry about the trig in a second. Cosine of pi over 2 times ln of pi over 2 plus sine of pi over 2 all over pi over 2. Okay, so this is going to be a little nasty, but we'll get through it. So sine of pi over 2. If you remember that from pre-calc, that's 1. So this is going to be pi over 2. Cosine of pi over 2, that's 0. Times ln of pi, that's still 0. So it's going to be 0 plus sine of pi over 2. We know that's 1. 1 over pi over 2. So this is going to be pi over 2. I'm going to reduce it a little bit. Times 1 over pi over 2. And that is 1. Now we are done. Now we are done. There you are. Okay. So notice what we did here. We used the full force of, in particular, it happened over here, right? We used the full force of our logarithms to be able to take the derivative of this thing, which we would not have been able to do otherwise unless we used the logarithms. Okay, this comes up pretty fairly often if you study higher math. This is actually one of the common tricks that gets pulled out of a sleeve when we need to prove a certain derivative. Okay, and I believe that is it. I think there might be a quick check right below here. So I want you guys to try this out. These are sort of the exact same idea. Don't be too scared about them. Try to run them through the same process that I did above, and it should fall in your lap, okay? And I think after that, it's blank, blank, blank till we get to lecture questions, okay? If you guys have any questions, I'll be in my drop-in Zoom times today from 3 to 6, as always. I will be answering emails right before that for them, probably the 2 hours before. Or you can, send me an email or talk to me through the discussion, however you want to do it. Just let me know, okay? Besides that, study hard. See you guys later.